Hello everyone. You can call me Nick. I am a graduate student here in Mapua University, and I enjoy pursuing projects for social good. Now, I'm going to cover a study entitled Event of Crime Against Property, Robbery and Theft Prediction using Probabilistic Graphical Model, or more particularly, Bayesian Networks. We'll start this presentation with a short background, our motivation behind the study, our assumptions. We'll then proceed with a summary of our methodology, and finally conclude with our results. Our study builds upon the idea that crime does not randomly occur. Based on a previous study, it is either planned or opportunistic. And since crimes does not occur at random, we believe that probabilistic models can be used to represent and infer based on our given data. Our data is a 5-year worth of crime records from 2010 to 2014 and is limited only to crimes against property with conviction, particularly on robbery and theft within Manila, Philippines. The goal in this study is to be able to preempt future robbery and theft incidents probabilistically at community level. The results from our proof of concept and its future iterations are envisioned to serve as a decision support for the National Police Agency and contribute to the improvement of their operations. This study was motivated by the fact that 54% of Filipinos are afraid that robbers might break into their homes. While it is perfectly normal to be afraid about being robbed, it is unfair for the people to be deprived of the feeling of security they deserve, even though these perceptions are just subjective. Through the findings from this study, we ought to make an impact on bringing down this 54% negative perception. Also, for our proof of concept, we focus on robbery and theft incidents because they are among the top contributor on the National Crime Index. Plus, they belong to the same crime category. Future studies may build on our proof of concept and take on other crime categories to contribute on our social mission. It has been proven time and time again that police visibility results in lower estimates of subjective risks of victimization. Therefore, our main goal for this study is to help the National Police Agency in their resource allocation and patrol route optimization by estimating the likelihood of robbery or theft incidents happening at the community level, so that they can strategically plan ahead. Currently, the patrol routes are statically scheduled day by day without dynamism, and police deployment is on demand, meaning the police will only respond whenever an incident is reported. By enabling them with future estimates of when and where a crime incident may probably occur, we envision their police operations will lean on being preemptive. Patrol routes will align with their estimates and should increase the perceived police visibility. Resource allocation will be aligned and should enable them to respond faster. That leads us to our objectives, which is to infer on the event of crime happening based on the joint probability distribution of the following data points from the given data: location, month, week of month, etc. Next is to recommend patrol route and schedule and resource allocation based on our inference or estimates. So, how are we going to approach our objectives? We need to handle uncertainty in a principled way. Based on the problem context, we are uncertain as to when and where a crime will happen, but each crime record provides us information. However, we are still never fully certain. Therefore, we need to leverage on the concept of probabilities. Here, we can quantify uncertainty in a principled manner. With probabilities, we can limit the infinite number of incidents and enable us to infer based on the information at hand through probabilistic models. Before I move forward with the methodology, I would like to share the reason as to why we are going with the Bayesian network with our problem, given the context. First, I like to share the two trends in data analysis. I agree that both frequentist and Bayesian philosophies can handle uncertainty. However, each handles it differently. In the frequentist philosophy, only repeatable random events has probabilities. For example, rolling a dice, tossing a coin, drawing a card, etc. These probabilities are equal to the long-term frequency of the occurrence of events in question. Probabilities are not attached to hypotheses or to any fixed and unknown values in general, whereas Bayesian philosophy views probability as a more general concept. We can use probabilities to represent uncertainty in any event or hypothesis. Here, it is acceptable to assign probabilities to a non-repeatable event like crime incident, which is mainly based on opportunity. Orthodox frequentist approach would claim that such probabilities does not make sense because the event is not repeatable. That is, we cannot simulate a crime incident over and over again and calculate the proportion of that crime being a success. Bayesian approach handles it by defining a probability distribution over the possible values of the mean and use sample data to update this distribution. Furthermore, traditional machine learning models conduct its predictions this way. It's like a black box processing input data and giving out its predictions. Data in, predictions out. Our problem context does not align with models that are deterministic in nature. In this slide, we show a non-exhaustive comparison of machine learning models over probabilistic models like Bayesian networks. In a black box machine learning models, our inferences are opaque, meaning its explainability is questionable. Models are constrained, meaning once we've trained the model, it is expensive for us to extend the model based on new gathered information. And its handling of uncertainty is questionable. While in probabilistic models, our inferences are clear and explainable via graph and probability theories and principles. Its models are flexible. We can easily update our models with new information since it is mainly based on probability distribution. And it can handle full uncertainty, no question about that. Okay, so now we can move forward to our proof of concept. For those that are encountering Bayes network for the first time, a lot of prerequisite knowledge are needed to fully understand the concept. Some relevant references are available in the full paper, but let me start by giving an overview of Bayesian network. It is a structure that can be represented as a directed acyclic graph. It allows compact representation of joint distribution from the chain rule of Bayes network. It also observes conditional independence relationships between vertices, nodes, or variables. In this kind of models, we have nodes that are probabilistically connected and not deterministically connected. Here, we are looking at causal analysis and probabilistic ways of describing relationships. And we should think Markov. The idea is that the nodes are explained by their immediate neighbors. For example, this node, day of week, can be explained by its immediate neighbor, like the month node and the week of month node. In principle, we can resolve the joint probability distribution down to its conditional probability or marginal probability. In our case, we are interested in the conditional probability of crime happening in a given location, as this will estimate future probability of crime happening in corresponding locations. We can apply enumeration or variable elimination method to resolve for probability distribution of our interest within the Bayes network. And it is solved by this system. But thanks to PJMPY, an open source Python package, it helps us avoid some nasty algebra and resolves this system programmatically. What I've done is a Python implementation of our model leveraging the said Python package to programmatically resolve the probability distributions of our interest, which is the probability distribution of a crime happening on a given location. And helped us conclude our inference based from our proof of concept. After some degree of further processing, we are able to infer about the location of crimes that will most likely occur given day of week and time of day. The results were summarized to display at the smallest administrative divisions level. Thank you all for listening. I'd like to end with a quote from George, a British statistician, that basically says that every single model will be wrong and can never represent the exact real behavior. However, even if it cannot describe the reality exactly, it could be very helpful if it is close enough. Here, in our model, we've been prudent on considering variables to make an inference. We are able to utilize past data to infer about probable future crime locations. Our inference can now serve as a decision support for the National Police Agency. Further iterations of this methodology may consider variations on historical data, meaning they can play around the length of time to be included. For example, they can consider only 3 months worth of data or a year worth of data, and evaluate the model's performance based on unseen data. That would be all from me. Have a nice day.